student Minghui Huang and my colleague Lipeng Lai at UC Davis. We wrote 2 papers on this topic, and both papers were published in ICML this year. Okay, so first let me introduce you what is optimal transport, and also a very closely related concept called Wasserstein distance. So what is a Wasserstein distance? Wasserstein distance measures the distance of 2 probability distributions. Okay, so for example, I have a figure here. In this red part, this is a probability distribution. So the integral of this curve, right, is equal to 1. And I have another probability distribution here denoted by mu. The integral is also equal to 1. Okay. So then basically, I want to measure the distance between these 2 probability distributions. So one way to measure the distance is called the Wasserstein distance. And this is actually a problem originated from Monge in 1781. The goal is to move one pair of sand to another pair. So assume that, for example, here in the red part, we have one pair of sand. Okay, we want to move these sand to this part, the blue part. Okay, now you see these 2 parts, they have the same volume. Okay, the integral both equal to 1. Right. So then we want to know how to move those sand, right, such that the total cost or the distance is minimized. Right. So that means we want to find an optimal transportation plan for these sands. We want to move these sands from this pair to this pair. Okay. So this is the so-called optimal transport problem, and the distance is called the Wasserstein distance. So optimal transport actually has a very long history. It has been studied by many very famous mathematicians, including some Fields Medal winners and the Nobel Prize winners. It draws a lot of attention recently because it found some very important applications in deep learning. So I assume that we all know this the generative adversarial network problem, the GAN problem, in the deep learning area. So basically, the original GAN uses the so-called Jensen-Shannon distance to measure the distance between 2 probability distributions. And then later, people proposed this Wasserstein GAN. So in Wasserstein GAN, they use the Wasserstein distance to measure the distance between 2 probability distributions. Okay, and the people already found that the Wasserstein GAN is more stable in the training of the neural network. All right. So now first let's look at this counter-Rovich relaxation of this Wasserstein distance problem or the optimal transport problem. We first consider the continuous case. So suppose we have 2 continuous probability distributions, mu and nu, and also we're given a cost function denoted by C. And the counter-Rovich problem is given by this. So this is basically the Wasserstein distance between mu and nu. Okay, so you can see here I have an integral here. So this part is actually to take the sum of the cost when you want to move, for example, when you want to move the sand, right, from X to Y, right? And this pi here, that's the transportation plan. Okay, so this notation here, this one we have a set. This is the set of all the joint distributions whose marginals are mu and nu. Now this is the continuous case. Now let's look at the discrete case. Suppose we have 2 discrete probability distributions. They're denoted by mu and nu. So for example, here in this figure, right, I have some red points and I also have some blue points. I want to move those red points to the blue points. Okay, and I want to know how to move them such that the total distance is minimized. Right? So here, this, for example, this probability distribution mu is defined as this. So here, xi and yj, they denote the supports of the probability distributions, and ai, bj, they are the probabilities. Okay. And also for this problem, we can very naturally define the cost function, right? So this is actually a constant matrix. When I want to move, the sand, right, from xi to yj, then this is the distance, right, and this is the cost. And our set pi, right, the joint distribution set becomes this set. So we have a set of n by n non-negative matrices, and it satisfies two linear equality constraints. Okay, so this one said that the row sum of this matrix is equal to A, and this one said that the column sum is equal to B. Okay, and A and B, there are the probabilities given these two probability distributions. And in this case, we can actually see that this optimal transport problem actually reduces to a linear programming problem, right? So here we're looking for this optimal transportation plan pi, and again, pi is n by n non-negative matrix. It satisfies the two equality constraints. Right? The objective function, we want to minimize the total distance or the total cost. Okay, so this is actually a very special linear programming problem. It is actually an assignment problem, and therefore it can be solved by the so-called Hungarian algorithm in this many time. Right? Okay. So one issue about optimal transport problem is that it is known that optimal transport suffers the crossover dimensionality. Now let me introduce you what is crossover dimensionality. So suppose we have two probability distributions, mu and nu, but they're unknown. We only have some sample data from these two probability distributions. So for example, we have sample data x1 up to xn from mu, and we also have some data y1 up to yn sampled from nu. Okay, and using those sampled data, we're able to define the empirical distribution. So we use mu hats and then nu hats to denote the empirical distributions. So then for these, for these two empirical distributions, so they are discrete, they are known, right? So then we can compute the Wasserstein distance between these two empirical distributions. So by just solving a linear programming problem. Okay, so then one very important question in the statistics is about the sample complexity of this approach. So you see, I want to compute the Wasserstein distance between mu and nu, but I don't know mu and nu, right? So that I don't know the Wasserstein distance between them. I can only compute the Wasserstein distance between these two empirical distributions, right? So then, of course, I want to know what is the error here, right? So apparently, this error is actually a function of the number of samples n, right? So imagine that you have enough number of samples, then it's very likely that your empirical distributions, they're very close to the original unknown distributions, right? So then this distance should be a very good approximation to the original distance, right? Okay, so actually people already proved this result. People actually proved that this error can be at this order. So let me just remind you, n is the number of sampled data, okay? And d is the dimensionality of the problem. Okay? So now if we, for example, consider the high dimensional case, that means the d is very, very large, okay? So when d is very, very large, then if you want this error to be small, then your n should be very, very large, okay? And that is called the crossover dimensionality, okay? And this is some problem in practice, because in practice it is possible that you don't have enough number of sample data, right? They're just not available, right? So then how to make this error small? Right? So that's one issue about the optimal transport problem. So to mitigate this crossover dimensionality, there are already some works, for this purpose. For example, this work by Riemannian et al. They proposed to use the so-called sliced approximation of optimal transports. Okay. Their idea is to project the data points, okay, your sampled data points, onto a given line, and then you compute the Wasserstein distance between these projected values. Okay, and this can serve as an approximation to the original Wasserstein distance. Okay, so the good thing of this approach is that you see, when you project the points onto a given line, so then you are actually considering a one-dimensional optimal transport problem. Okay, so one-dimensional optimal transport problem is easy. Okay? It can be computed very efficiently, right? Of course, in practice, we don't know which line to project the points onto. Right? So then, in practice, they suggest that hey, you can draw several random lines, right? And for each line, you can compute this approximate Wasserstein distance, and then you take the average and use that average value as the approximation to the original Wasserstein distance. So recently, in 2 papers by Patty and Couturier and Newsweed and Rgas, they generalized this idea. They suggested to project the data point to a k-dimensional subspace. Okay, so when you project the data to a given line, it's like you project the data to a one-dimensional space. Okay. So then they suggested to project to a k-dimensional subspace. Okay, k is bigger than 1, but k is still very small. All right, and this leads to the projection robust Wasserstein distance. All right, now let's look at this projection robust Wasserstein distance. The projection robust Wasserstein distance is defined in this way. Let me explain to you this notation here. This E here, this is a k-dimensional subspace. Okay, it belongs to this calligraphic GK, and GK is a Grassmann manifold. It is the set of the k-dimensional subspaces in RD. Right. So then, for example, this part, it means that we want to project the data from the probability distribution mu onto this k-dimensional subspace E, right? And we also want to project data from nu to the subspace E. And then we compute, this is W2, right? That's the Wasserstein distance. We compute the Wasserstein distance between these 2 projected data. Okay, and then of course in practice we don't know what is the best E to project the data onto, right? So then we now here consider a worst case scenario. So we want to find the subspace E such that the Wasserstein distance between the projected data is maximized. Okay. In this paper by Newsweed and Rgas, they actually proved that for this spiked transport model, this projection robust Wasserstein distance can indeed improve the sample complexity. Okay, it actually can improve the sample complexity from this. This is for the original Wasserstein distance. Okay, improve the complexity from this quantity to this quantity. And remember, the D is the dimensionality of the problem. Okay, and K is the dimensionality of the subspace. Okay. For example, let's say, for example, your D is equal to 1,000, right? Then if you want to make this quantity small, your N should be very, very large, right? But K is much smaller than D. Right? So K, for example, K can be equal to 2 or 3 or 5. Okay, it's not very large. Then to make this quantity small, you don't need N to be very large. Okay, so in this sense, basically this projection robust Wasserstein distance can indeed mitigate the crossover dimensionality issue. Okay, of course, the next very important question is how to compute this projection robust Wasserstein distance, right? Okay, now let's, for example, look at the discrete case. In the discrete case, so here, this part, right? Let's maybe return to the previous slide. So this is the definition of the projection robust Wasserstein distance, right? We have a maximization problem here with respect to the subspace, right? And this part, that's the Wasserstein distance. Okay, that's the Wasserstein distance. And the Wasserstein distance, if we consider the discrete case, we know that it corresponds to a linear programming problem. Right? So then this part, this is a minimization problem, and the descent variable is pi. That's the optimal transportation plan. Okay? And the red part here, this is actually the distance between the projected data. So originally I have xi and yj. There's the original data. And then here I have a matrix U. Okay, U transpose xi minus yj, the 2 norm squared. This is actually the distance between the projected data. And what is U? U is actually an orthonormal basis of the subspace E. Okay, so in this optimization problem, I actually replaced the k-dimensional subspace E by its orthonormal basis. And so U is a D by K matrix, and it is orthogonal. Okay, and in the literature of Riemannian optimization, this constraint is also known as the Stiefel manifold constraint, and it is non-convex, right? So then you can see that basically to compute the projection robust Wasserstein distance, this is a max mean problem, and also there's some non-convex constraint. So it looks like very challenging to solve. Right? Okay.
So can I
yes.
can I have a question here?
Sure. Yeah.
So in your previous slides, you said your k can be very small, right? You can somehow alleviate this case of a dimensionality problem,
That's
right?
Yes.
But in your bound, so improve to the power 1 over d to 1 over k, right? So in that bound, is there any other constant depend on k? It looks like if your k is smaller, then your min-max problem is easier, right?
K is a smaller.
It looks like
that's right. Yeah, of course. Then you consider a smaller. So the variable here is small, right? So yeah.
Yes, and also your
bound
bound is
optimization
better,
problem.
right?
Sorry. What's your question?
Then your bound in your previous slides, that is the power 1 over k, right? Negative 1 over k, and this bound becomes better, right?
That's right.
So that means you solve a easier problem, you can get a better bound. Is there some constant hidden in this big O depend on k?
Okay, I'm not sure about that. But let's see. Even okay, I'm not sure if there is for example some polynomial function here about k. Yeah.
But you can pick say k even equals 1.
Yeah, I think you're right. So it seems that right. So when k is small, then this bound is better, right?
Yes. And the problem becomes easier, right?
Right.
So in their control, in their upper bound formula, there is some ck. I think it depends on the dimension.
Yeah, there may be some.
Yeah, I think that's right. I think that's reasonable. Yeah.
Yeah. Otherwise, yeah.
Right. Yeah, I think you're right. Yeah, I better to check the paper more carefully later. Yeah.
Okay. Thanks.
Okay. Okay. Now let me continue. So now let's focus on how to solve this max min problem. Okay. There is one existing work tackling this problem. This is the work by Tianyi Lin and his courses from UC Berkeley. They actually proposed a method. It is called Rgas, the Riemannian gradient ascent algorithm, meets synchronous algorithm. Okay. So their idea is actually very natural. So for example, let's return to the previous slide. See here, for the minimization problem here, right? Suppose I can solve this problem optimally. Then I found the optimal solution pi, right? Then the optimal function will be a function of u, right? So then if you look at the maximization problem here, you're maximizing a function of u subject to a Stiefel manifold constraint, right? Then of course a very natural idea is to apply the Riemannian gradient ascent algorithm, right? It is ascent because I'm maximizing the function, right? However, there's one issue left, because when you look at the function here with respect to u, it is possible that this function is not differentiable, right? So that you cannot compute the gradient. Right? Okay. So in this Rgas algorithm, Lin et al. They proposed the following modification. So basically, they add an entropy regularizer to the minimization part. Okay. So the entropy function h is defined as this. This is the function of pi, and eta here is a positive parameter, right? So it is known that this entropy function h here, it is strongly convex over this constraint set. So when this function becomes strongly convex, then we minimize this function. Of course, we know that the optimal solution is unique, right? When the optimal solution is unique, then for this function with respect to u, it is differentiable. Okay. So then we denote this function as f eta of u. So then if you look at the maximization parts, we're actually maximizing this function with respect to u over a Stiefel manifold constraint. Okay. So then the idea will be very straightforward. So in Rgas, we just update u in this way. So what is this? This is actually the Riemannian gradient ascent algorithm. So every iteration you just compute the Riemannian gradient. Okay, this blue part denotes the Riemannian gradient of the function at eta at uk. Then in the Riemannian optimization, so we're maximizing or minimizing the function over a smooth surface. So it's like that when you take the gradient step, you're outside of the feasible region, right? So the retraction operation can bring the iterator back to the surface, back to the manifold. Okay. So this is just a standard procedure in the Riemannian optimization literature. All right. So this is the Riemannian gradient ascent algorithm. There is one issue left. So every iteration, when you need to compute this Riemannian gradient, okay, the Riemannian gradient of f eta at uk, you actually need to solve this minimization problem exactly, right? So for fixed u equal to uk, right? And this problem is known as the entropy regularized optimal transport problem, right? And to solve this problem, there is a widely used approach. It is called the synchronous algorithm. So the synchronous algorithm actually solves the due problem of that entropy regularized optimal transport problem. It solves the due problem using the alternating maximization algorithm. Okay. So now let's briefly look at this synchronous algorithm. So this is the entropy regularized optimal transport problem. The decision variable is pi. Pi is a n by n non-negative matrix, and it satisfies two linear equality constraints. Now for these two linear equalities, I introduce the Lagrange multipliers, and I denote them as alpha and beta. Then I can write down the due problem. It turns out that the due problem of this one is given here. So this is a maximization problem with respect to alpha and beta. Okay, and you can see that this problem is actually unconstrained, right? And there are two block variables. So very naturally, we can use the alternating maximization algorithm to solve this problem. So alternating maximization means that every iteration I just fix one variable and I maximize the function with respect to the other variable. Okay. So for example, I fix alpha, I maximize this function for beta, right? And then I fix beta, I maximize this function for alpha. And the advantage of this synchronous algorithm is that this function, okay, this function is easy to maximize when you only maximize it for one variable with the other variable fixed. Okay, actually, each of the subproblems actually admits easily computable closed form solutions. Right. Okay, so now, once you solve this due problem, right, you obtain, for example, alpha star, beta star, then you can actually recover the optimal primal solution here, pi star. And using the pi star, you're able to compute the Riemannian gradient of this function at beta. And then that's how this Rgas algorithm works. Is there any question? Yes.
Yeah, can I ask a naive question? So
Sure.
for this Rgas, right? After the entropy regularization, is that the upper bound, or the cursive dimensionality bound is still correct? Because the entropy regularization really depends on how much entropy you add on, right? It could be very far away from these two.
Yes, I think you're right. So you mean after you add this this entropy regularizer, right? Whether this complex is still correct?
Yeah.
Yeah. So this bound will be different.
Yeah.
Yeah, it is different. But actually, in this Rgas paper, they can actually prove this. They prove that okay. So basically, for example, for the original problem, right? I'm not looking for the exact optimal solution. I'm looking for epsilon stationary point. This is a non-convex problem, right? So I'm looking for epsilon stationary point, and they can actually prove that if this eta is chosen at the same order as epsilon, then the epsilon stationary point of this problem will be also epsilon stationary point for the original problem. So actually,
okay.
The algorithm is designed for solving this problem, but eventually they can prove that the solution that they obtained is the epsilon station point for the original problem.
Mm. Yeah, thanks.
Right. Okay. All right. So then let's summarize this Rgas algorithm, right? So every iteration we need to use this the Riemannian gradient ascent, right, to update the UK. And in order to compute this Riemannian gradient, we need to solve the entropy regularized optimal transport problem. And then we use the synchronous algorithm to do that. We use the synchronous algorithm to solve the dual, and from the optimal solution of the dual problem, we can recover the optimal primal solution, the pi star. Then of course you can notice that if you use this synchronous algorithm in every iteration, right? It is an iterative algorithm, right? You need to run many iterations until it finds the optimal solution here, right? It can still be very expensive, right? So our approach is actually based on some observation. We actually found that we use the synchronous algorithm, right? It does the alternative maximization. We actually found that one iteration of the alternative maximization is good enough. Okay, so it is like when you solve the dual problem, you just fix alpha, you update the beta, then you fix beta, you update the alpha, then that's it. Then you do the Riemannian gradient ascent step. So that gives our algorithm. That is our Riemannian block coordinate descent algorithm. So now let me introduce our algorithm. So our algorithm is also based on a reformulation of the entropy regularized projection robust Wasserstein distance problem. So we consider the same entropy regularized problem, right? So this is the entropy regularized problem. And then we look at this minimization parts. We know that this is a strongly convex problem, right? And for this blue part, we can write down its Lagrangian dual problem, right? We use alpha and beta to denote the Lagrange multipliers for these two equality constraints, right? And then the Lagrangian dual of this blue part is given by this. And then for this minimization part, now you see your variable pi, right? There is no constraint. And for this minimization problem, actually we know that it admits a closed form solution given by this. Okay. Now, if you just plug this expression back into the objective function here, then you no longer have pi. Right? You only have a function with respect to alpha and beta. Okay. So then, if we do that, then this Lagrangian dual problem actually reduced to a maximization problem here. All right. So then we know that you see this blue part is equivalent to this blue part, right? So then I can actually replace this blue part by this blue part. And then if I do that, then I no longer have a max-min problem. I actually have a max problem, right? And then I have 3 block variables. I have a u, it is subject to a Stiefel manifold constraints, and I have 2 other block variables, alpha and beta, right? Okay, so finally, for this problem, right? So we know that it is just a purely maximization problem, right? And for the ease of presentation, we can just rewrite this as a minimization problem, right? We consider the negative of the objective function here. We denote the objective function here as function g, and it has the 3 block variables, alpha, beta, and u, right? And then we know that this kind of problem actually is suitable for the BCD method. All right. Okay. So then this is our remaining BCD algorithm for minimizing this function g. First step, we fix beta and u, we minimize the function for alpha. And then we fix alpha and u, we minimize the function for beta. And the last step, we actually do a remaining gradient ascent step for the variable u. So here in the first 2 steps, we can do the exact minimization because we found that they are actually the same as the steps in the synchronous algorithm. And these 2 subproblems, they admit easily computable closed form solutions. And for the last block u, we cannot do the exact minimization. So we only do a gradient ascent step. All right, so this is our main algorithm, the Riemannian BCD algorithm. Okay, and we can actually prove that our Riemannian BCD algorithm found an epsilon stationary point to the original problem. Okay, so this is what I just said. So when we prove the the convergence results, right? So we prove that we found an epsilon stationary point to the original problem. There is no entropy regularizer here, right? Okay. Now let me first introduce our definition to the epsilon 1, epsilon 2 stationary points. So we call pi hat u hat epsilon stationary points if these two inequalities are satisfied. Right? Now let me explain these two inequalities. So the first inequality here, it actually said that if pi hat is given, then u hat is good, because when you compute the Riemannian gradients of the objective function, right, with respect to u, this gradient is small. It is smaller than epsilon 1. The second inequality said that if u hat is given, then pi hat is good, because for the pi variable, right? So the function value error is bounded by epsilon 2. All right. So this is our definition to the epsilon 1, epsilon 2 stationary points. Then this is our main convergence results. The first one, this is about the iteration complexity. We can actually show that if we run our Riemannian BCD algorithm for this many iterations, we actually found an epsilon 1, epsilon 2 stationary points of the original, the unregularized, right, projection robust Wasserstein distance problem. And for each iteration, we can actually also compute the arithmetic operations complexity, and then multiplying with the number of iterations here, we can actually compute the total arithmetic operations complexity of our algorithm for obtaining an epsilon 1, epsilon 2 stationary point. And this complexity is given here. Okay, so now we can compare these results with the Rgas algorithm. We just compare a special case for which it's easier to do the comparison. We consider the case where epsilon 1, epsilon 2 are equal to each other, and they're both equal to epsilon. The complexity for the Rgas algorithm, it is actually in this order. In terms of epsilon, you can see that it is in the order of epsilon to the negative 12. So this can be huge. Right? For our algorithm, the Riemannian BCD algorithm, we can show that the complexity bound reduced to this order. So in terms of epsilon, this is epsilon to the negative 3. And so we can conclude that the complexity bound of our method is significantly better than the existing Rgas algorithm. Okay, now let me show you some numerical results. In the first experiments, we tested the algorithm on some synthetic data. We consider a uniform distribution over a hypercube, and in this one, we actually define the transportation plan. Okay, so that we know the optimal transport. We know the exact Wasserstein distance. Okay. In this case, so I show some numerical results here. There are two rows here. In the first row, it corresponds to the case where n is equal to 100. So n is the number of sampled data. Okay. So basically, for example, in each of the figure, you want to move these red points to the blue points. Okay. And for each pair of points, if there is a line, then it means that you will move some mass from the red point to that blue point. The second row, it corresponds to the case where n is equal to 250. So we have more sample data, right? So clearly you can see more sample data here, right? Comparing with this one. In the first column, these are the optimal transportation plan given by the Wasserstein distance. Okay. And these two, they're the projection robust Wasserstein distance computed by the Rgas algorithm. And the last column, there is the optimal transportation plan computed by our Riemannian BCD algorithm. So you can see that these optimal transportation plans, they're they look very similar, right? Especially for the Rgas and the RBCD algorithms, because they solve the same problem. So their optimal transportation plans look almost the same, right? Okay, so the next experiment. So we still consider the same problem. For this problem, because we know the optimal transportation plan, we know the exact Wasserstein distance. So then we can actually compute the error between the computed Wasserstein distance and the exact Wasserstein distance. Okay. So then here we actually want to show the show a graph where the y-axis denotes the error, and the x-axis denotes the number of sampled data. That's little n, right? So here we have three curves. Here we have a blue curve, we have orange curve. They correspond to the projection robust Wasserstein distance computed by two different algorithms. And this green curve, that's the original Wasserstein distance. Right? So then we can see that, for example, if you have the same number of sampled data, then the error given by the projection robust Wasserstein distance is much smaller than the Wasserstein distance. Okay. So in this sense, we actually demonstrated that the projection robust Wasserstein distance can indeed mitigate the curse of dimensionality. Okay, for example, if you want to achieve the same error, then if you use the projection robust Wasserstein distance, you don't need a very large number of sample data. Okay, so the next data sets we consider two Gaussian distributions. For these two Gaussian distributions, we actually can also compute the exact Wasserstein distance. So here in this figure, we want to show the robustness of the projection robust Wasserstein distance against the noise. Okay. So the y-axis is still some kind of error, and the x-axis it denotes the noise. We can see that when the noise level is large, right? So then these curves, right, the green one and the orange one, right, their errors are much smaller than the blue one. So the blue one is the Wasserstein distance, and the orange one and the green one, they're the projection robust Wasserstein distance. Okay. So using this figure, we actually show that this projection robust Wasserstein distance is indeed more robust to the noise. Okay, we also did some CPU time comparison. So we compared our RBCD algorithm with Rgas, and also another method called the Frank-Wolf method. I didn't have time to explain this one. So basically, this projection robust Wasserstein distance problem, it actually has a convex relaxation, and the people proposed to use the Frank-Wolf method to solve that convex relaxation. And from these comparisons, we can actually see that the Frank-Wolf method is much slower than the other two algorithms. And among all these three algorithms, our Riemannian BCD algorithm is always the fastest one. And this actually is consistent with our convergence analysis, right? We showed that our RBCD is faster in terms of the total arithmetic operations complexity. All right. Yes.
Can I ask another question? So in terms of
Sure.
noise, right? So you compare with the original distance without the entropy regularization, but your approach using the entropy regularization. So is that the Wasserstein, the blue curve is the without the entropy, right? As a true distance.
That's right. So you just solve the original linear programming problem.
So yeah. But my question is, so this sort of robust to noise, is that because of the entropy regularization, or is because of the
I think it is because of the projection. So I think basically you can imagine that you see for the projection robust Wasserstein distance, right? The first step is we need to project the sample data to some smaller, lower dimensional subspace, right?
Yes.
So when you do the projection, actually you also project the noise, right? So then you actually basically you removed some noise in the higher dimensional space.
but the noise in that k dimension still maintains, which means you essentially for that k dimension you solve the noisy problem, which
that's right.
is
That's
the
right.
same as
for the original problem, you also have noise.
Yeah, that is right. But I guess maybe entropy
I think,
plays something.
yeah, my feeling is that this is due to the projection procedure, I guess.
Okay.
Yeah.
Okay. But the other
So
thing
let's
is
see, for example, let's say, for example, right, you project the data onto, for example, onto a line, right? That's a one-dimensional subspace.
Yes.
Then
Yes.
basically you only, I think you only preserve some parts of the noise, and there's some other parts actually you, right? For example, that if that's in the orthogonal space, I think that part is removed already.
That's right, but the thing is that in that k dimension, noise still there. In that k dimension, you presumably, if no entropy regulation, you presumably solve exactly the same problem, if no entropy regulation. So
that's right. That's right.
If the noise still maintained in that k dimension, you still have the noisy version.
Mm-hmm.
But
right,
of course,
right.
you have the entropy.
So I think So in both cases, of course. So both problems are still noised. But it seems to me that after you do the projection, right? So when consider the the problem in the k-dimensional subspace, then I think you have less noise. Is that right?
Well, it's hard to say. If you only take a look at that k dimension, the noise level is about the same, right? Of course, in the higher dimension, it's different.
Right. That's right.
Or let me put this way: for this projected case, if you tune the entropy regulation parameter like very, very small, will you observe still very robust, or it will be less robust than the bigger?
Okay. So that's a very good question. So actually in the algorithm, in the synchronous algorithm, so people cannot use a very small regularizer, parameter. That will cause some numerical issue. Right. So that
exactly
this eta, right? This eta cannot be very, very small. So
Yeah.
usually we need to maintain eta as a reasonable level. Right. So
when you apply this RBCD, you don't have to have the entropy. Or why you still need to have entropy?
No. We have the entropy. So RBCD is also for the entropy problem.
Yeah, but you don't have to, right? Or you do?
We do. So if you see, if we do not have this entropy regularizer, then we don't have this equivalent form here.
I
So
see.
so then you see, this is a max-min problem, right? It's like a saddle points problem. If I don't have this term, then I cannot equivalently rewrite this max.
Oh, I see. I know what you mean. You cannot plug it. You cannot solve and plug it. Okay.
That's right. So I think so for both our algorithm, the RBCD, and also the Rgas algorithm, we both design an algorithm for the entropy regularized problem.
Yeah,
it's just then when we prove the convergence, we actually show that the epsilon station point for this problem is also epsilon station point for the original problem.
I see. Thanks.
Okay, sure. Okay, let me continue. All right. So here in this part, I want to show you some real data. Here we have a corpus of 7 movie scripts. So for each movie, it has some scripts, right? So then for those scripts, you can think of that they form a probability distribution. Okay, so for each movie there is a probability distribution, and for the scripts, of course, it contains a lot of words, right? So those words can be viewed as sampled data from the probability distribution. Okay? And for each movie, suppose you have a lot of sampled words, and then using those sampled words, you can compute the Wasserstein distance or the projection robust Wasserstein distance between those sampled words, right? And in that way, you can actually measure the distance between two movies. You can measure whether they are close to each other or not. Right? So here we have 7 movies. In this table, let's only focus on the lower bottom part. Okay, this part. We don't look at this part. This part is about the CPU time. Let's just ignore this part first. We only look at this part. So this part is about the projection of bus and distance between the two movies. And in each cell, we have 2 numbers. These 2 numbers are actually the projection of bus and distance obtained by the 2 different algorithms. One is our RBCD algorithm. The other one is the Rgas algorithm. And we actually see that the value these 2 algorithms got are actually almost the same in all the cases. So just look at one of them. All right. So now let's, for example, look at the first column here. The first column we have movie D, and there are some other movies. Right? So we compute their corresponding projection of and distances. And in this first column, let's find the smallest value. It turns out that this one is the smallest value. So that means in terms of the projection robust and distance, D and T, they're very close. Okay, comparing with the other movies. Now let's look at so what is D, what is T? So D is Dunkirk, and T is Titanic. Okay, I think this really makes a lot of sense because we know that these 2 movies, they're both about ocean, right? They're about boat. So you can imagine that in their scripts, right, they actually share a lot of common words. So if you compute the Wasserstein distance, they are close. Let's look at another example. For example, this KB1, that's QB1, and KB2, that's QB volume 2. Okay. So basically, they should be similar, right? They should be close. And let's see whether that's the case. So this is KB1, and these are 3 numbers, right? So that's those are the distances between KB1 and the other 3 movies here. And also we look at these 3 numbers. So these are the distance between KB1 and these 3 movies, right? So among these 3 numbers and these 3 numbers, we found that this one is the smallest one. So that means the KB1 and KB2, they are indeed the closest one among all these big pairs. All right. So I hope that you're using this example to show you that this projection robust and distance really makes sense in practice. Right. So this is about another data set. This is called the amnesty data set. We know that amnesty actually contains a lot of images, right? Each image corresponds to handwritten digits from 0, 1 up to 9, right? So then for each digit, we can think of that the images, right, corresponding to the same digits, they are actually sample data from the same probability distribution. And using those sample data, if we compute their Wasserstein distance, we can measure the closeness between the 2 digits. Right? So then, for example, let's look at some of the examples here. So for example, this is digit 1, right? This column, so it shows the optimal, the projection robust Wasserstein distances between 1 and some other digits, right? And we found that this one is the smallest one. So this is digit 7. So that means 1 and 7, they're very close. Okay, so that's also very consistent with our intuition, right? So in practice, if you do handwriting, 1 and 7, they're very easy to be confused. They're indeed close. Okay. All right. So I think I still have some time. I'll just briefly introduce another topic. It is called the Wasserstein Barycenter. This is related to what we have just talked about Wasserstein distance. Okay. So what is Wasserstein Barycenter? Let's think of the following question. So if you're given a set of probability measures, what is their mean? So for example, you see, if you're given some numbers, that you know how to compute the mean, right? Or if you're given some data points, right? You also know how to compute the mean, right? It's like a clustering problem, right? You want to find the center. Okay. Now let's say imagine that hey, what if the given thing, right? So there are a set of probability measures. So then what is their mean, right? So then one way to define the mean of the probability measures is the so-called Wasserstein-Barycenter. So Wasserstein-Barycenter is the measure that minimizes the sum of the Wasserstein distances of it to each of the measures in the set. So first of all, you want the mean to be still a probability measure, right? And you want the distance, right, between all these given probability measures to the center. You want this distance to be minimized, right? And this is useful when we want to aggregate information from several probability measures or histograms. A motivating application is to summarize the data from multiple sources. So for example, in this picture, see on the ground, I have a lot of sensors, right? These sensors, they can gather data from the same environments, but with possibly different noise distributions. Okay. So then you see, for each sensor, the sensor collects some data, right? All these data, they will be sent to this communication tower. Okay. And this tower will collect all these data and then assemble them into a single signal, right? And then it is like for each of sensor, right, you have a probability distribution, right? And for each distribution, you have some sample data, right? And you want to find one single probability measure such that it is close to the average or to the mean of these probability distributions. And that is the Wasserstein-Barycenter. As another example here, let's look at this figure here. So I have 5 rows and 6 columns. So in total, I have 30 images here, and in each image I actually have 2 ellipsoids. So now I want to compute the mean of these 30 images. Okay. So then this is a one computed by the Wasserstein-Barycenter. You can see that in this figure, I clearly have 2 ellipsoids, right? So it's it is close to the mean of these pictures. Right? It makes sense. These 4 figures, so there is a mean computed using some other approaches, and you can clearly see that they don't give you very useful information. Right? They don't make much sense. Right? Okay. So then let's look at the definition of this Wasserstein-Barycenter. So what is how to mathematically define the Wasserstein-Barycenter? So suppose you're given m probability measures, right? mu1, mu2 up to mu m. You want to find another probability measure denoted by nu, and that's actually the Wasserstein-Barycenter. You want to find a nu such that you compute the Wasserstein distance, right, between mu l and nu. And for these distances, you compute their weighted sum, right? And you want to find a nu such that this weighted sum is minimized. Okay, so that's how to find the Wasserstein-Barycenter. Of course, as we discussed before, this Wasserstein distance, right? That's actually equivalent to the optimal transport problem. So the Wasserstein distance actually suffers the crossover dimensionality. Right? Now for the Wasserstein-Barycenter problem, it is defined as the weighted sum of the Wasserstein distances. So then you can naturally imagine that, well, it is very likely that this Wasserstein-Barycenter also suffers the crossover dimensionality. Right? So we want to mitigate the effect of crossover dimensionality. Then what do we do? So we use the same idea, right? We want to, instead of using the Wasserstein distance here, we want to use the projection robust Wasserstein distance. Okay. So then the projection robust Wasserstein-Barycenter problem that we propose is the following. So for the in the original definition of the Wasserstein-Barycenter problem, there is this Wasserstein distance, right? We just replace this Wasserstein distance by the projection robust Wasserstein distance. But this definition actually gives us a very challenging optimization problem. So you see, we have an inf here, we have a sup here, we have another inf here, right? So it looks very challenging to solve. So then in practice, we want to consider some relaxations. So we consider 2 kinds of relaxations. The first relaxation is we assume that all these EL here, they are all the same. Okay, what is EL? So let's see. You have the sample data XL. That's from the distribution mu L, right? And for those sample data, you want to project them to a k-dimensional subspace EL. Now, our first relaxation said that we assume that these k-dimensional subspaces, they are the same, all right? So the second relaxation is we want to switch the order of this soup and the first inf. So then it is like we are considering some kind of dual problem for this problem. Okay, of course there is a duality gap because this problem is non-convex, right? And only that way we can design an algorithm for solving this problem. And after these two relaxations, this is our relaxed PRWB problem. Okay, the relaxed projection robust Wasserstein Barycenter problem. I'll just skip some details. If I look at the discrete case of this problem, it is actually very similar to the projection robust Wasserstein distance problem we discussed before. Okay, so we have a max mean problem, right? And for the mean part, that's actually a linear programming problem with respect to pi. And for the max part, we have a matrix U. It satisfies the Stiefel manifold constraint. So then we can use the similar idea as what we did in the projection robust Wasserstein distance problem, right? So we can design this Riemannian BCD algorithm, and similar to the work by Lin et al., we can also design the Rgas algorithm. Okay, and that's what we did in our paper. So we proposed the Riemannian gradient ascent method, and also another method, the Riemannian BCD method, for solving this relaxed projection robust Wasserstein Barycenter problem. So they're quite similar to the previous one. So I'll just skip those details. And finally, let me just show you some numerical results. Okay. So again, this paper, so it actually shows the similar results as the previous study. We want to actually show that our proposed relaxed projection robust Wasserstein Barycenter model is more robust to the noise than the original Wasserstein Barycenter. Okay. So again, in this figure, we compare the error versus the noise level. Okay. So again, we found that by using the proposed model, the relaxed projection robust Wasserstein Barycenter, okay, computed by two different algorithms, the errors are smaller than the original one. Okay, than the original Wasserstein Barycenter problem. Okay, so the next one we want to show that our proposed model indeed has the potential to mitigate the effect of the crossover dimensionality. Okay, so again we compare the error versus the number of samples. Okay, and again we found that the curve, the errors computed by the new proposed model, the errors are smaller than the original model, the original Wasserstein Barycenter model. Okay. Finally, I want to talk about one application. This is called the discrete distribution clustering. Okay. So we will mainly consider the approach proposed in this paper, Ye et al. In 2017. So for example, if you're given a set of data points, right? You want to do the clustering. Then how do you do it? A widely adopted approach is the Kmeans approach, right? So in Kmeans, actually, each iteration you do actually two steps, right? One step is for each cluster, you need to compute its center, right? And then after you compute the center, then you need to assign each of the data points, right, to the closest center or the closest cluster, right? And that's it, right? So that's how Kmeans works. Now let's consider the following case. So instead of giving a set of data points, you're actually giving a set of discrete distributions. You want to cluster those discrete distributions into the correct clusters. Okay. So then in this paper, Ye et al., they actually proposed to apply the Kmeans idea to probability distribution cluster. Okay. So then there are two steps in every iteration. The first step, for each cluster, you need to compute its mean, right? Its center. Now the center becomes the Wasserstein Barycenter, okay? Because the data points become the discrete distributions, right? The second step, for each of the distribution measure, you need to assign it to the nearest center, right? The nearest cluster, right? Then how do you measure the distance, right? Because you want to find the nearest one, right? How do you measure the distance? You use the Wasserstein distance, right? So as you can see, each iteration in the step one, you need to compute the Wasserstein Barycenter, right? So as we demonstrated that, so our relaxed PR Wasserstein Barycenter is likely to be better than the Wasserstein Barycenter. So then we propose to replace this Wasserstein Barycenter here by our proposed model, the relaxed projection robust Wasserstein Barycenter. Okay, and these are some comparison results we conducted. These two figures, they correspond to different data sets. Let's just look at one of them. The y-axis denotes the classification quality. So basically, we want this number to be large. Okay, and there are two curves. The orange one, that's our projection robust discrete distribution clustering, and the blue one is the original one proposed by Ye et al. And then we can clearly see that by replacing the Wasserstein Barycenter by our new model, right, the relaxed projection robust Wasserstein Barycenter, we can do much better, okay, in both cases. All right, so now let me just conclude. So in this work, we considered the projection robust Wasserstein distance and the projection robust Wasserstein Barycenter. The main goal was to mitigate the effect of the curse of dimensionality of the optimal transport problem. We designed the algorithms for both problems. The algorithms were based on some novel reformulation of the entropy regularized problem. So more specifically, we proposed the Riemannian BCD algorithm, and we analyzed the arithmetic operations complexity, and we found that it is significantly better than the existing method, Rgas. Okay, and we conducted some numerical results. Basically, we want to deliver the following messages. The first one is the projection robust models. They're indeed more robust to the noise, and they have the better sample complexity. And finally, when we incorporate our projection robust Wasserstein Barycenter model to this discrete distribution clustering, we found that it can perform much better than the original approach. Okay, so with that, I will stop here, and thank you very much for listening. And now I'm open for questions.